Hi there, welcome to my next video on the PAT where I'm going to be discussing mechanics. I reckon a lot of the things that are in front of you on the syllabus here, you will already have extensively covered in school, but just as a warning, because these are topics you are expected to be very familiar with, the questions can be quite tricky. So just on to the first concept, I'm just going to be discussing speed, distance, velocity, acceleration, their relationships. So these different values, I'm sure that you're aware that some of them are vectors and some of them are scalars, and I'm sure you know what that means. Vectors are something that has both magnitude and direction, and then a scalar is something that only takes into account the magnitude. So things such as energy, they're not going to be vectors because it is a physical quantity. You can't have negative energy, particularly, and energy doesn't act in a direction. Your velocity might act in a direction, but your energy doesn't. If we just imagine a velocity that has two different components, an I component and a J component, or you can imagine this as a Y component and an X component, if that's easier to imagine. Then we could say for every 10 that it moves in the J direction, it moves 6 in the I direction. And this is how we would represent our velocity as a vector. But if we are after the kind of resultant speed, in a sense, we need to work out the magnitude of this. And the magnitude is not just 6 plus 10. That doesn't make sense. Your magnitude would describe its kind of speed in a kind of relative direction. So this would be in this kind of direction along here. So we would use Pythagoras to work out what the speed would be, and it would come out to that. So that is the magnitude of the velocity, which is the speed. And then for our direction, we would use SOHCAHTOA. I didn't bother to actually work out what that angle was, but you can if you want. Okay, and then another relationship that's really important to know regarding displacement, velocity, and acceleration are how they relate to each other in a calculus sense, I suppose. So if we call the displacement x, then the first derivative of x would be the velocity. And that does make sense because what that's saying is that the rate of change of displacement is velocity, which should make sense. It's how quickly we change displacement, essentially. And then our second derivative of our displacement is our acceleration. And that also makes sense because if we think of our acceleration as the first derivative of our velocity, then yeah, it's the rate of change of velocity, isn't it? It's how our velocity changes in a given space of time. So if I were just to give an example, so if we just say that our displacement is 3t squared plus 2t plus 1. So that is how we are moving with respect to time. If we take the first derivative of that, then we get our velocity, which is 6t plus 2. And then if we take the second derivative, we have an acceleration of 6. So looking at what's happening here, our displacement will look something like this. It's something that's increasing in gradient as our velocity here would describe. And it's essentially a t-squared graph. A notable feature is to notice that the gradient isn't constant as well. And we see this because our gradient is changing with t here. So it's increasing with t. And that's how we know that this graph is somewhat correct. And then if we plot out the velocity against time, we can see it's just a straight line graph, which makes sense, and also makes sense because our gradient is a constant. And then if we plot out our acceleration against time, then this will just be a straight line because it's just a constant 6. So if we apply these ideas and concepts to questions, then a kind of immediate place to start would be Suvat equations. This question here is talking about a car that's driving along, and then a cat jumps out in front of the car, and we need to know how much force we need to apply to stop the car in time. So essentially what that's telling us is that we need to break from u meters per second to 0 meters per second in t seconds. But we don't know t yet. And we need an expression for t. So I've just drawn a little diagram here of a car and a cat, and then that is the initial distance between them. If we set out our Suvat equations, we can see that the values that we have are, we want our final velocity to be 0. Our initial velocity is u. We don't know the acceleration. We don't know how long it'll take, but we do know the distance. So we have 3 bits of information here. And a useful bit of information that we want is this t here. And you might be wondering why I'm saying that. So the question is asking us for a force. And in this circumstance, our force would be the rate of change of momentum. So we know some information about the momentum. We know that we are going to be going from mu to n times naught. So our change of momentum will be something, will be mu essentially, or minus mu, depending on which way around you're looking at it. But we don't know anything about the time that it'll take yet to break. So, because it'll be something like change in momentum over change in time is our force. So we need to know some information about time. So we can use this first equation here, the S equals ut plus half at squared, to get d equals ut plus half at squared. But again, we don't know anything about a. So we need another equation to find a. And for that, we can use v equals u plus at. We can stick in our values. So v was naught, u is u, a is unknown, and then t is also unknown. So we can get an expression for a in terms of t. And we can pop that back into our equation over here. And then rearrange this and get an expression for t. And then we said earlier that our force is our rate of change of momentum. So it's our change in velocity over our change in time, all multiplied by our mass, because mass times change in velocity is change in momentum, and then change in time is change in time. So we can say that our mass times u minus 0, which is our change in velocity, divided by our time, 2d over u, is mu squared over 2d. And that is our answer, A over here. Don't worry too much about the signs. That's just saying that it's a braking force. So it'll act in this direction to slow us down. Okay, so this next question is a projectile question. And again, I'm sure you've seen plenty of questions like this. So what's happening is we have a projectile that's being flung off a cliff at this certain angle here with this initial velocity. And it's going to go through several stages. What's going to happen is it's going to go from A to B. So it'll go from its point from the top of the cliff up to its highest possible point. Then from that highest possible point, it'll go from B to C, which is essentially a mirrored position to what we had earlier, which means that this will take the same amount of time as this will. And then finally, we'll go from C to D, which is to the ground from the cliff. The cliff is 10 meters high. So we have some information about this projectile, but we also need to bear in mind that we're traveling down at the same angle here as the 30 degrees. As we normally do with our projectiles, we need to know what our vertical and horizontal components of velocity are. Our vertical component will help us work out when it'll stop up here. And our horizontal component, I don't think we need it in this question, but it'll tell us essentially how far we've traveled across. But we're not being asked about that, so I'm probably not going to touch the horizontal velocity at all. But our vertical velocity, using a bit of trig, we can work out that it is 10 sine 30, or 5 meters per second. So we need to work out how long it'll take to go from 5 meters per second to 0 meters per second up the top at B here. And we can just use one of our Suvat equations to do that. I chose V equals U plus AT and rearranged it for T, and then stuck in the numbers and got half a second. And then, like I said, so the next part of the journey, B to C, it is mirrored. So it'll take the same amount of time. So it'll take 0.5 seconds as well. So it'll take half a second as well. So finally, in looking at C to D, we need to work out how long it will take to fall 10 meters when our initial velocity is our vertical component at this point here, C. So we use trig again to work out that our initial velocity is minus 10 sine theta, because we do need to take into account the direction here. Otherwise, it will mess up our Suvat equations. And then I've used this S equals UT plus half AT squared to rearrange and get this quadratic equation in T. So we get two answers for T. One is positive, one is negative. And you may be like, how can you get negative time? Well, essentially, what that is describing, so our T is 1 is describing this point here. But our T is minus 2 is actually describing the point all the way back here, if we imagine before it had fallen, all the way down here when it would be at the same position, because it's mirrored, essentially. But we don't care about that. We only care about this T is 1. So that means altogether, our first part of the journey was half a second, our second part of the journey was half a second, and our last part of the journey was 1 second. So the total would be 2 seconds. And that answers our question. Okay, so our next section is on graph interpretation. And some of these questions can be really, really tricky. But if I remember correctly, I don't think this question was too bad to start with. So a car is initially stationary. At time t0, it starts to move at a speed v1 for a time delta t1. Immediately after this, it moves at a speed v2, which is greater than v1, for a time of delta t2, which is less than delta t1. After this time, it is stationary again. So using this information, we need to sketch a velocity time graph. And we need to remember to label our axes. It's very kind that it's reminded us that. But this question is fairly straightforward. So initially the car is stationary. So we have some period here where the car is stationary. And then at this time, t is 0, it starts to move at speed v1. And it's a constant speed, or constant velocity if you'd rather, for a time delta t1. So the time at this point here would be t0 plus delta t1. And then it speeds up instantly and moves at a speed v2, which is greater than v1. So we wanted to plot it higher. And then this happens for delta t2 seconds. So the time at this point here would be this time plus the amount of time it took to get there. So t0 plus delta t1 plus delta t2. Okay, so then from our graph, we need to determine an average speed while it is moving. And they've given us some numbers as well, but I'll neglect the numbers until we have an idea about the average speed. So when we think of an average speed, we need to kind of, I feel like the best way to imagine how to work out an average speed is to say, well, for this portion of the journey, we traveled at this speed. So for this portion of the journey, we traveled at this speed. And then for this portion of the journey, we traveled at this speed. So we need to know what our average is from the total journey. So our change in times, essentially, are just portions or percentages of the journey, if you'd like, out of a total journey. I can Actually, I can prove this idea by just looking at a portion of the journey at a time. So say we just look at the amount of time described by delta t1, right? So this section here. If I say, well, the portion of the journey that I was traveling at v1 was v1 times delta t1, described by the total amount of the journey described during this time, so delta t1, our average velocity would just be v1, which makes sense because we've only traveled at v1, so it's got to be our average velocity. And then you can do the same thing for the latter part of the journey if you'd like. But the easiest way I can try and imagine it is that you have v1 for a blob of time. So we multiply these together to get kind of their weighting. And then we have v2 for another blob of time, and then that's its weighting. And then we can average those out over the total weighting of the entire journey, which was delta t1 plus delta t2. So just sticking the numbers in, we end up with 4/3 meters per second. Okay, next it wants us to draw a speed versus distance graph. So for this, we need to kind of change our mentality a little bit and read what's going on in the question. So what this is telling us that we're traveling 1 meter per second for 2 seconds. So that means we travel 2 meters at 1 meter per second. And then later we're moving at 2 meters per second for 1 second. So that also means that we're traveling 2 meters, but this time at 2 meters per second. So if we plot this, we say, okay, we're traveling 2 meters at 1 meter per second. And then we're traveling a further 2 meters at 2 meters per second. Okay, so next it's asking, from the second graph, find the average speed, Vs, known as the distance weighted average. Again, express Vs as a formula using these symbols, and then we can stick in the numbers, I suppose. This is a similar idea to the previous question where, we want to find out the weighting. So where we want to find out the average. And for the first one, what we used we used our time as our weighting. But this time we want to do the same thing, but using our distance as our weighting. So what we say is the portion of the journey in distance that we traveled at V1 would be V1 times delta S1. And then the portion of the journey distance-wise that we traveled at V2 would be V2 times delta S2. And then we want to divide that by the entire length of the journey. So I've just stuck in the numbers again, and then we end up with 3/2 meters per second. Okay, so now it's asking which of the two averages, VT or VS, is equivalent to the conventional definition of average speed, which we assume to be VC is total distance traveled over total time taken. This question is certainly designed to trick us because we see total distance traveled, and then that kind of makes us think of this part here. But really, the clue that we are looking for is the total time taken on the bottom. Because in our first definition, we have the total time on the bottom. And then if you think about what a velocity times a time gives you, well, if we look at that in terms of units, we have meters, which describes distance. So in this question, we actually have this sum of distances divided by this total time, which is what this equation here describes. And you could also think of that in the sense that what we did up here was we looked at the area of these when we multiplied the velocity with the time, or the change in time. We worked out the area of these, and the area of a velocity time graph, I'm sure you know, gives the distance traveled. So for this question, we can say that VT is the same as VC. And then finally, it asks us to state a mathematical operation that should be applied to a curve. So taking into account what we just said, that this total distance traveled comes from finding the area underneath the graph. The mathematical operation that finds us the area underneath a curve, I'm sure you remember from the calculus video, would be integration. So our equation for VC would be integral of the speed with respect to time over the total time. Okay, now this next question is really quite complicated and hard to get your head around. So I'm warning you in advance for this one. I've also only decided to do the part A of this question because it's an extremely long question. And I think I'll do another video where I go through more complicated or like notoriously bad questions in the PAT and go through examples of them. But this question here gives us a force distance graph, which is probably something we're less familiar with. And we have a point mass of 1 kilogram that starts from rest at point x0 is 10 meters and moves without any friction under a force F, which depends on the coordinate x, as illustrated in the figure below. And the motion is confined to one dimension along x. So at this x0 here, our speed is 0. But we have a force of -10 applied to it. And the first part is asking us what its speed is at x is equal to 0. From x is x0, or x is 10 if you'd rather, to x is 0, we've traveled 10 meters under a force of -10 newtons. So thinking about that, it's probably easier to imagine this question in the context of energy as opposed to any suvats or anything like that. So we can say that our work done is our force times distance, right? Or the area, if you prefer, under this graph here. So from x is 10 to x is 0, we've traveled a distance of 10 meters under a force of 10. So our energy or work done would be 100 joules. And then if we imagine that all of that work is converted to kinetic energy, we can say that our kinetic energy, half mv squared, is equal to 100, and then rearrange that to get a quantity for our velocity at 0. And we can kind of assume that we've done the correct thing here because the next question is asking us to sketch its kinetic energy as a function of x. From the previous part, we said that this area under here is the work done. And if we say that's all converted to kinetic energy, then it would imply that our graph for our kinetic energy would be essentially a function of this area here. So if we start at 0, let's say, then our area is increasing as we move to the right. And then if we move to the left, our area decreases until it gets to 0. And then it increases again beyond that 0. And this is a constant increase. And this is a non-constant decrease and increase. So if we come down here, we can come up with equations to describe this area if we'd like. So like we did in the previous question, we can use integrals to work out the area. So our equation under here is essentially f is -10. It doesn't change with x. So if we say when x is greater than 0, our equation for force with respect to x is just -10. It doesn't change whatever the value of x is. So if we integrate this, then we end up with fx plus c. And don't forget that when you integrate, you have to add your constant on the end if you don't have bounds. And this constant just describes our initial value, essentially, for kinetic energy. So at x is 0, we worked out from the previous question that our kinetic energy was 100 joules. So if we can say at x is 0, so minus 10 times 0 plus c is 100. And then that gives us a value for our c, and our c is just plus 100. So our kinetic energy when x is greater than 0 is 100 minus 10x. And then if we do the same thing, looking at the graph for x is less than 0, if we come up with an equation for this line here, we can work out the gradient is -1, and then our y-intercept, sorry, I've used c twice here, but it's essentially, it's a y-intercept technically both times, but this is our y-intercept for this graph here. So we can say that our equation for our graph is f equals minus x minus 10. And then if we integrate that to get an expression for the area, we end up with x squared over 2 plus 10x plus c, and that's all negative. And then again, we know that at x is 0, the kinetic energy is 100. So if we just pop in x is 0 here, then we get that minus c is 100, so c is minus 100. So we can pop this minus 100 into our equation to get an expression for kinetic energy, which is minus x squared over 2 minus 10x plus 100. And then we can plot these two graphs. So when x is more than 0, we have this straight line graph, essentially. And then when x is less than 100, we have this curve here, which is described by this. We can also work out where the maximum kinetic energy happens by taking the first derivative of this here. But we already know that the first derivative is the equation of the line. And then setting that 0. So we can see here that the maximum will happen when x is minus 10, because this is our first derivative. And to find out the maximum, we set it to 0 and find that value. So it's minus 10. So we know that the maximum occurs at minus 10. And then we can also use this equation here to work out where the graph will hit y, or kinetic energy, is 0. So I've done the maths over here. I had to use the quadratic formula because it's a complicated one to factorize, but I ended up being 0 when x is minus 10 root 3. So we know some important information about the graph here. Okay, and next we need to sketch its velocity as well as its acceleration as a function of time. Now, this is a little bit more complicated. So we have some graphs over here, some clean graphs. But we need to try and work out what's going on here. So initially, we're displaced at 10 meters with a force of minus 10 newtons. So if we say this is our center point here, our mass has been shifted over 10, but it's being acted on by this kind of pulling force. It's trying to pull it back into the center. And then because of that force, it accelerates towards the origin. And then at the origin, it still has this force of minus 10, right? So it's still being pulled to the left. But when it gets to this point here, it has no net force, essentially. So it's stopped accelerating when it's at minus 10. And then it begins to have a force in the other direction. So it's caused to accelerate back to the right. So at the origin, it accelerates to the left, but the rate of acceleration is decreasing until it's 0 at x is minus 10. So at that point, it has no net force and it's not accelerating anymore. It's moving at a constant velocity to the left. And then as it displaces further to the left, we get a gradually increasing force to the right. So that means that we're decelerating until, well, this point that I've calculated here. And that was where our kinetic energy was 0. So we're still moving to the left until this point here where it is at a standstill. And then at minus 27 meters, we have no kinetic energy, so we are not moving, but we still have this force to the right here. So we're still, but we're being pulled that way. So that means that we are going to begin to accelerate in the other direction. And this is where on this graph, essentially, we've gone like this, and then we bounce the other direction. And what is this describing? Well, it's describing simple harmonic motion, where we have this kind of swinging left and right. And we'll end up with a graph that looks something like this. So yeah, this is where the question moves on to a part B, which is even more complicated again. But like I said, I'll cover that in a different video where I'll be going over some particularly tricky questions in the PAT. Okay, so the next part on the syllabus is response to forces. And this includes Newton's second law and vector addition. So after that previous question, we have quite a simple one here. And we have a mass that's on 3 strings lying on a horizontal table. The strings exert forces outwards on the mass as shown below, but the mass does not move. And we want to find the relationship between the forces A, B, and C, essentially. So if our mass is not moving, what does that imply? That would imply that our net force is equal to 0. So if we use Newton's second law in all of the directions, so if we take the horizontal forces here, we can say that the net horizontal force is 0. So that means that A has to be equal to the horizontal component of C. So A is equal to C cos 45, and we end up with C is root A, because it asked us to find an equation for C in terms of A. So we had to make sure that we rearranged it as an equation of C in terms of A. And then the next part, we want to do a force balance in the vertical direction. This tells us that B is equal to the vertical component of C. So B is equal to C sine 45. So C is root 2B. But this time it was asking us for the relationship between A and B. So we can replace C with what we worked out C to be in terms of A up here, and then simplify it down, and we get B is equal to A, or A is equal to B. Okay, circular motion. I think circular motion was something that I hadn't actually covered in school yet before the PAT. So I hope you've studied it, because it can be a little bit tricky to get your head around. But this question, I remember this being quite complicated as well. But a child of mass m stands on a platform which rotates freely at angular speed omega. The child's center of mass is initially at a radius r0 from the axis of the platform, as shown in the figure below. The child now slowly puts itself closer to the center of the platform. So it says, state the minimal force Fr needed to pull the child closer to the center as a function of the radius r, the child's center of mass. So when we think of the minimal force needed, essentially what we need to say is we need to look at kind of the edge where something happens, right? So we need to know what the force this child is fighting against is. So this child is trying to pull itself inwards, but it has some kind of force, centripetal force, forcing it outwards as it spins around. So if you imagine yourself on a child's roundabout ride, you would feel this force pushing you outwards. And it's the premise of a lot of fairground rides as well. You know, the ones with the fast spinning around and you end up being slammed against the wall. Well, that's centripetal force that's causing you to be slammed outwards. And it is described as m mu squared r. So depending where you are along here, so depending how far away you are from the center of the r, you'll experience a different size force. So the boundary where we're moving or we're not moving happens when our resultant force is 0. So this is like the boundary where we're still, and anything greater than this will cause us to move inside. So if we use Newton's second law, we can say that the resultant force of the system is mass times acceleration. So our Fr, our pulling force, minus our centripetal force will be equal to 0 on this boundary. So the value that we need to kind of exceed to move inwards for Fr would be equal to m mu squared r. So this question gives us quite a large hint that we need to use calculus to come up with an expression for our work. But if we try and instinctively think about what work is, then it would be our force that we use to act against whatever. So it might be friction, it might be, well, the centripetal force, for example. But it's the force that we're using to move multiplied by the distance that we move. But in this case, our force that we're using to move is not constant. It changes depending how far away we are from the center, because the amount of force that we need to move changes as we get closer or further from the center. So the further we are from the center, the more force we need to pull ourselves forwards. And then as we get closer and closer to the center, it becomes easier and easier. So we can't just multiply F, this force here, we can't just multiply that by our distance traveled, because it's changing as our distance changes, because it essentially looks like this. So the area underneath, if we say that's r, our distance, our total, so that's r naught, the total distance we had to travel. And the best way I can describe this is kind of looking at it graphically. So if we say this is r and this is our force, well, our force changes something like this with r, and say we traveled a total r naught. But our work would technically be the area underneath this graph here. But to just multiply Fr by r naught would not give us this area under here. It would give us this kind of total area over here, which is not useful. So this is why we need to use our mathematical operation integration to find this area underneath. We integrate our force with respect to r, our distance from the center, and then we worked out what this kind of minimum value was over here. So we can just stick that in. Okay, so next it's asking, into which form of energy is the child's work converted, and what will qualitatively happen to the angular speed omega as the child approaches the center? So we are using this work in order to move. And what is the movement energy? That would be kinetic energy. So we are converting to kinetic energy. And then what will happen as the child approaches the center? I think the easiest way to kind of interpret what's happening there is to imagine an example, right? So as we move closer and closer to the center, our angular velocity is actually going to increase because of conservation of angular momentum. And I think a prime example of where this happens is if you imagine a ballerina or a figure skater as they do a pirouette. So as their body and their arms and legs are extended, they travel slower. So they kind of spin around a lot slower. And then as they come to bring their arms and legs in, they spin far, far faster. And that's because their angular momentum is conserved. This next part kind of goes into the conservation of angular momentum. But yeah, that's essentially why, as we get closer to the center, it acts as this ballerina who's pulled their arms into their body. So the angular momentum, J, of the system of child and platform is conserved. It is defined as J is I omega, where I is the moment of inertia of the process, which goes which is given by I equals mr squared plus IP, where IP is the constant moment of inertial of the platform. I think that's meant to say inertia. Find the expression for the angular speed omega r as a function of the radius r. So there's a lot going on here. There's a lot of information that you don't really need to know. It's honestly just subbing in equations. So they've told us that J is I omega and I is mr squared plus IP. So we can stick in this value for I in here. And then we just rearrange it for omega. So you don't need to understand what any of that is. You just need to be able to rearrange an equation. Okay, so next it's asking us to find the total work done by the child when it has reached R0. So as it's traveling from the outside here into the inside, what is its total work? So we said previously that the work was the integral of m omega squared r. But at this point, we know that omega isn't a constant. It is also changing with r. So we have to take that into account in our integral. So if we just stick in what we said omega was, so omega squared changes to j squared over m r squared plus ip all squared. We can stick that into our equation and then rearrange this equation to look like this. And then at this point, we can see that it is kind of identical to what's here, where our A is IP over M. And then we can just stick in that integral. And remember that it's between your you perform the integral between your two bounds. So here we're saying that we're traveling from R0 to 0. So those are our two bounds. Our upper bound or our larger value being R0 and our lower bound being 0. So we're integrating between R0 and 0. And then we come up with this expression here from this that they told us. Hi, this is editing me. I think this video's gone on long enough, so I'm gonna hold it here and I'll see you in part B of mechanics in the next.